All right, so the problem of the day I gave you guys yesterday I thought was pretty challenging.
Yeah, that was me.
I don't think it was mean, I just thought it was challenging. So there were quite a few different ways you could go about doing this. I'll show you guys the way I was thinking of.
Oh yeah, please do.
And the first step I was thinking of was we need to convert this ketone to some sort of carbonyl group that can undergo acyl substitution. Ketones do not. So, first thing I did was I converted it into an ester. What reagent do we need to do this? A peroxy acid. And what's this reaction called? Does anybody remember the name? A Baeyer-Villiger. All right. And then the next step, what I did, hey, let's make sure everyone can hear you guys. So diaval H, I ring open the ester into the aldehyde. Do you have a question?
Yeah, what do you want to understand is the mechanism for like the summary?
Mm-hmm.
You didn't specify the word had oxidation alcohol. I don't know how to explain it. They didn't have two O's.
When we went over the sheet yesterday, I showed some simple conversions to esters and then away from esters. The Baeyer-Villiger oxidation was from last chapter, though, where you can convert from a ketone directly to an ester. So that was in chapter 20, I believe. All right, why didn't I just add a Grignard reagent directly to my ester? What was that, Eddie? So that's one option. What's another reason? You get a mixture, right? So if we tried to react a Grignard reagent with this ester, it would add in uncontrollably. It would add in twice because your first intermediate would be a ketone that's actually more reactive than your ester. So in this case, we can't just hit it with a Grignard reagent. We have to kind of dance around a little bit before we can do that. All right, so the next thing I'm going to do is add in trimethyl silyl-chloride. And why am I adding this on? It's a protecting group. So in this case, we need to protect that alcohol, especially if we're going to be doing a Grignard reaction. So I'm going to react this with methyl magnesium bromide and water. And so we've protected our alcohol. It's not going to deprotonate. And we end up with a secondary alcohol. What do you guys think the next step should be? I heard somebody say PCC.
Adrian said it.
Good job, Adrian.
So we can oxidize our secondary alcohol back down to a ketone. And then what's our last step? TBAF. We need to remove our protecting group. So as we get closer to the ACS exam, I'm going to be pulling reactions from previous chapters and previous terms. So in this case, I wanted you guys to remember protecting group strategies and Baeyer-Villiger oxidation.
On the ACS, is it called DMSCL and PCC, or does it use its full name? Or?
I believe so. We'll actually start doing some practice problems. I need to take a look at the exam myself because I haven't opened it up in quite a while. If you have the practice book, I would try to go through those practice problems. That way you can familiarize yourself with how they ask questions. Sometimes with multiple choice exams, it has a lot to do with how familiar you are with the layout and the way they ask questions, more so than even necessarily knowing the material. Because if the more familiar and comfortable you are with the layout, the better off you'll be. Same thing with SATs too. I was reading that your SAT score statistically goes up like over 100 points after you take it the first time. It's just because you've seen the material before and you're more comfortable with it. All right. So now let's go back to chapter 21. And today we're going to move on to amides. And we've already seen preparation of amides a couple of times. The preparation is really straightforward. We can just convert an acid chloride directly to an amide. And what reagent do we need? Ammonia, right? So we need NH3, and we need two equivalents because it acts as its own base, and we can directly prepare an amide. In this case, it works best with acid chlorides. Or acid halides, I should say. Why don't we see it very often with esters? Does anybody have an idea why we normally see it with acid halides instead of esters? So in this case, chloride's a much, much better leaving group than an alkoxide, right? So acid halides are much more electrophilic. They're much better at doing nucleophilic acyl substitution than esters. So normally when we see preparation of amides, we see it with acid halides. All right, I've got an example too that I wanted to show you. I like seeing real world examples of some of these. So we've got two amino groups coming off the benzene in the 1 and 4 position. And then we're going to couple this let me move the plus over. There we go. With an acid halide. What do you think will happen if we mix these two together? You can almost think of this as being Velcro ends, right? We're going to be creating a bunch of amide bonds, and in particular, we're going to polymerize it. So you can actually make a big polymer. And when you do this, you make a polymer where the linkages are all amide bonds. Clean this up a little bit. And what I do to show repeating units is I bracket it, and then I put a little n down there to just say that it's going to repeat over and over again. This is a really, really cool polymer. This is Kevlar. So Kevlar is amazing. It was discovered, I believe, in the mid-50s or early 60s. And I actually have a video.
Why is it so? Can you explain why it's so strong?
You go, just for a second, yeah. Are you going to show us the video now?
Yeah, I'll show you guys the video. But before I do that, too, I'll tell you guys a little bit about Kevlar. When they were testing it, it had some really bizarre physical properties due to the strength of the amide bonds in it. And they found out that it has tensile strength 5 times stronger than steel, which makes it an incredibly powerful material for being strong, and it's very, very lightweight. Let me see where I added this. I had a link on here. Sorry, let me attach my keyboard here. And I'll actually pull up the video just manually. Let me plug in the sound here. So I was reading about the development of Kevlar, and one problem the Defense Department had was that prior body armor were literally steel plates. And if you're a Marine or a person in the Army, do you want to walk around all day with a steel plate on your chest? No. So this allows soldiers much more mobility and protection. However, if you get shot with a gun wearing a Kevlar vest, you're going to get some broken ribs and a really, really nasty bruise. It'll just prevent puncture going through the vest itself. So it's a pretty impressive polymer. The one thing that I think is really cool about Kevlar that a lot of people overlook is its utility in satellites and spacecraft. So if you're looking at the space shuttle, one big problem that the space shuttle faces is what they call micrometeorites, or just space debris, because you can have things orbiting around the Earth that are the size of maybe a pea, going thousands of miles an hour. And if this hits your spacecraft, it could cause catastrophic damage. So the outer hull of most satellites and spacecraft are actually wrapped in Kevlar to prevent puncture of the spacecraft and keep them nice and safe.
How do you find out that they could do that with it?
Usually when you make polymers, you test all the physical properties of them after you make them. So in this case, they made Kevlar and they realized, wow, this is some incredible stuff. We need to start putting it into things. Yeah, it's kind of one of those miracle polymers, I think. Very fascinating. All right, where did I put my pen? There it is. All right. So really, this is the main way we're going to see for making amides. We'll cover peptides a little bit later on in the quarter. But we can continue on and see reactions of amides. Oh, there's the link. I'll leave it on the bottom of the page. Actually, come on. I'd want to move it. There we go. I'll move it right below the picture here. All right, sorry. Just wanted to get it out of the way there. All right, the reactions for amides are very similar to what we've seen before. The first reaction involves taking an amide, reacting it with acid. And when you do this under high temperature conditions, you can convert your acid into your amide into a carboxylic acid. And you end up with an ammonium ion, which gets protonated by the acid. Do you guys want to see the mechanism for this?
Sure. Do we need to know
It's very similar to one we saw in our problem of the day that we already had.
it? Do we need to know it?
Yep.
Okay, well then, yeah.
It's one we've seen before. But we'll go and review it. Okay, so if we react this with acid, first step will be our carbonyl getting protonated. Once we have our carbonyl protonated, we can react this with water. And water will just add into our carbonyl. And then we can have another molecule of water do a proton transfer. where it will grab this proton off of the water that just added in. And we end up with our hydrate. And this can act as a proton donor back to the amine. And I always like to show these using separate steps, not an intramolecular proton transfer. And then we have the malicious shove, where the oxygen lone pair can kick down and shove off our amine. And ammonia was our leaving group. And ammonia's got a lone pair that's pretty basic. So it will participate in that last proton transfer. Plus our ammonium ion. So very similar to what we saw in chapter 20. In fact, I had you guys do this on problem of the day just to make sure that you guys were drawing your arrows correctly. All right, so the reaction we saw was up here was our base catalyzed hydrolysis. So I'm going to label this, or sorry, acid catalyzed hydrolysis. There's also the base catalyzed version. Base catalyzed hydrolysis. Sorry, just wanted to check. And with base catalyzed hydrolysis, it's a very similar procedure. You have your amine, but this time it's 2 steps. You take sodium hydroxide, you run this under a high temperature condition, and then at the end you need to reprotonate. So you add in dilute acid. And again, you can get to your carboxylic acid. The mechanism for this is a little bit different. The hydroxide will just immediately attack your carbonyl, kick up electrons. The oxygen will kick off your amide. And this is a pretty terrible leaving group, which is why you have to add so much heat to it. Because when it gets ejected off, you've got a nitrogen with a negative charge. So this is really quite a poor leaving group, and in fact, it'll immediately come and grab a proton back from your carboxylic acid. And that's why in the next step, you have to add in your acid to reprotonate your carboxylic acid. So in each of these hydrolysis reactions, you have to add quite a bit of heat, which is a good thing because amide bonds make up the structure of all of our proteins and enzymes. We don't want them to be cleaved very easily. So the only way we can cleave them in a lab is by using strong acid or strong base and cranking up the temperature. All right, there was one last one that I wanted to cover, or actually a couple others.
Okay, base, yeah.
The next one we have is reduction. And so if we have our amide, you can reduce it all the way down to the amine. And what reagent do you think we need? Not quite. So you're thinking of the Clemenson reduction, which is another reducing technique. But in this case, we're adding on 2 hydrides. That'll be a hint.
Oh, that was on the quiz.
Yeah, lithium aluminum hydride. We need something that can readily donate hydride. So we'll add excess. And then during our reaction workup, we'll add water. So we don't need to know the mechanism for this, but it's kind of strange because you lose your oxygen off of there and you end up with your primary amine. All right. So now let's go make a reaction map, just kind of like we've done in the previous chapters. So we said the main way to make amides was from acid chlorides, and we add in ammonia, and we need 2 equivalents at least, and we can form our amide. Then from here we can go to our carboxylic acid, and we can do this 2 different ways. We can either add acid and crank up the heat, or we can add base, crank up the heat, and then quench with acid. Both of those will work to interconvert between our amide to our carboxylic acid. The next one we saw can convert it back to our primary amine.
Is one more favorable for the above, for the carboxylic acid, or is just whatever you feel like doing?
It depends on the conditions. If you do have acid-sensitive functional groups, you want to choose the appropriate one, and same if you have base-sensitive functional groups. The other option we have is we can reduce it using lithium aluminum hydride, followed by water. And then the last one that we're going to cover next is we can convert it into a nitrile by using thionyl chloride, and we're going to cover that mechanism here shortly. But the reaction map for amides is pretty small. They're not as synthetically useful. All right, so let's continue on to nitriles. So we've already seen the preparation of nitriles a few times. All right, the first one was via an SN2 mechanism. So if we have some sort of leaving group off of an alkyl chain, we can react this with sodium cyanide. And we can directly make our nitrile group. So same SN2 rules apply. You have to have a primary or methyl alkyl halide. It won't work if you've got a tertiary alkyl halide. The backside attack is too hindered. The other route we said was from amides. So if we have an amide, we said that we needed thionyl chloride. And if you do this, you can directly make your nitrile. And then what's the byproduct from the thionyl chloride reaction? SO2 is the driving force, so we can include that in there. And then also HCl. All right, so let's take a look at the mechanism. Because it's a little bit different. Thionyl chloride is one of the best electrophiles ever. So what can happen is the lone pair from the nitrogen can dump down. One of the pi bonds can jump up, and then a lone pair from the oxygen comes over, and we kick up electrons. So it's a bit steppy. 4 different arrows. And you've got an oxygen right there. It's now bound to a sulfur. Okay, so what do you think happens next? It's pretty similar to what we've seen before.
Malicious.
You're on the right track. Yeah, kick off a chlorine. We've got a really, really great leaving group right there. So this will kick down, shove off a chlorine. Form a sulfur-oxygen double bond. And now we can react it with a generic base. You could even show chloride doing this. I'm just going to show it as B. And this will come deprotonate. And we're almost there. One more equivalent of base. We'll come and grab this proton, which will cause a cascading effect, where we'll clamp down here, and then kick off our chlorine. So kind of like a Jacob's ladder. And you end up forming your nitrile directly, plus your SO2 gas. And so the driving force for that last step is formation of sulfur dioxide gas. Okay. So we've seen 2 different ways to prepare nitriles. You can either do it from acid or alkyl halides, or you can do it directly from an amide. But let's see what we can do with nitriles. So the first reaction is, again, hydrolysis. Oop. And it's very, very similar to the amide hydrolysis. You can take a nitrile, react this with strong acid and heat. And this will take you to your amide. And if we add more acid and heat, you can take this all the way to your carboxylic acid. Typically, if you wanted to stop at the amide, you'd choose a different synthetic route. you typically see hydrolysis where it goes straight to the carboxylic acid. Alternatively, you can take a nitrile and use sodium hydroxide and heat, just like we saw with amides, followed by an acidic workup. And this will give you your carboxylic acid directly. So we can interconvert pretty readily. This is very similar to the amide mechanism, so I'm not going to re-show everything. Okay, the next one is looking at addition of Grignard reagents. And this is a kind of neat reaction. You can take a nitrile, react this with a Grignard reagent, and I'm going to call this R prime, and then treat it with acid. And you can go directly to your ketone. So let's try to figure out what's going on here. This at first drives people kind of nuts because they don't see how it pieces together, but the mechanism's pretty straightforward. So if we've got a Grignard reagent, it can add directly into this carbon, kick up electrons onto that nitrogen. Now you've got nitrogen with 2 lone pairs, and your R prime group added in. Now if we add acid, that nitrogen's going to come and grab a proton, kick off water, and voila, what do we call this guy? An imine, right? So the product when you add a Grignard to a nitrile is an imine. But if it's in acidic conditions, what's going to happen to the imine? Yeah, it'll keep on protonating, and we can actually show hydrolysis of our imine. So just for kicks, let's show the mechanism. This is exactly what we saw in the previous chapter, where water can add into our imine. And I'm going to take a shortcut here. I'm just going to say plus or minus H plus to show the proton transfer. So we're going to transfer a proton from that alcohol over to the amine. And we can kick off our amine.
Should there be 2 hydrogens on the nitrogen, on the one on the left?
Yeah, so I'm showing the proton transfer from the alcohol, or the water that added in. So essentially what I'll highlight it. We're going to move this proton here over here.
On the left, on the first yellow one, look to the nitrogen.
Oh, yes, thank you. Good catch. So this should be H3N. There we go. Let me clean this up a little bit. So we'll kick off our ammonia. And the ammonia will come and deprotonate. And you end up with your ketone plus an ammonium ion. So it's using chemistry we've already seen in previous chapters. But it's a pretty useful tool towards making highly connected molecules. Just react a Grignard with a nitrile group. All right, we've got one more reaction for nitriles. Last reaction of the chapter, actually. And this is reduction. So if you take a nitrile, just like with amides, you can convert this to a primary amine. And with amides, what reagent did we need? LAH, right? So we need lithium aluminum hydride, and we need excess, and then we add water. All right. So these were two pretty quick ones. I think the most useful reaction out of these nitrile reactions is the reaction with the Grignard, because you can use that to create highly connected molecules. All right, so let's make our reaction map. So if we have an alkyl halide and we want to go to a nitrile, what reagents do we need? We're going to treat X as a leaving group. Kareem, what do you think?
So, I think that we are going to. Not going to even tell you.
So we've got an electrophile. We need to react it with the nucleophile, which in this case is going to be sodium cyanide, so that Cn minus can come kick off that leaving group and do an SN2 substitution. What reagent do we need to convert between the amide to a nitrile? Thionyl chloride. That was one of our new reactions that we saw today. So we can use thionyl chloride to go directly to a nitrile. And then we can interconvert this to a carboxylic acid using two different routes. We've already seen these before. You can use acid and heat, or you can do base and heat. And if you do the base route, you've got to follow it up with an acidic workup. And then what about if we want a ketone? A Grignard. So I'll call this R prime MgX. 2 will be water. And then what about going to an amine? Yep. Lithium aluminum hydride. And we need excess. And then we follow it by adding in water. So it's a pretty straightforward procedure. All right. So that's the meat of chapter 21. One thing we will start doing more of is combining synthesis problems. But before we do that, we want to come up with synthesis strategies. So typically what I do that you guys are already picking up on is for this chapter, I like to make reaction maps. So the way I do this is we've got acid chlorides, we've got anhydrides, we've got esters, and amides, and we can fit nitriles in. But what I try to do is I try to connect the dots to all of these. And so, for example, I could say, what reagents do I need to convert an acid chloride to an acid anhydride? Not quite the acid, but really close. The acetate, right? So in this case, we would say, all right, for this one, we would need the acetate. If we want to go to the ester, what do we need? The alcohol. And if we want to go to the amide, what do we need? Ammonia. And so what I do is I try to make a map of these, and we can keep on going and we can say, all right, what about going from an anhydride to an ester? Well, that's an alcohol, pretty straightforward. And then we could go from an anhydride to an amide, and this would take ammonia to equivalents. And it starts to get pretty repetitive once you go through this multiple times. But what I like to do is just make my own map. I'll leave it up to you guys how you want to organize it. And I encourage you guys to share with one another too. So if you come up with a really nice map, maybe show your friends how you laid it out and see if you can come up with some big three-dimensional, or not even three-dimensional, two-dimensional map where you can try to connect a lot of these reactions that we've learned. If you try to just brute force memorize section by section, it'll be a lot more uncomfortable than trying to piece it together as a map. I know it's still a lot of work, but bear with me on that. All right, so for the new problem of the day, I took it a little bit easy on you guys. A little bit easier than yesterday. This one's a synthesis warm-up problem for tomorrow. Tomorrow we're going to be doing synthesis problems that incorporate chapter 21. This one is asking you to start with benzene and use other reagents. In particular, you're going to have to use some reagents from chapter 19 and then some reactions from this chapter as well. I gave you guys a hint the other day, and so I'll reiterate this hint. How is this group normally attached, and what is it called? Oh man. This is an acyl group. And how do we do that? In this case, we normally use acid anhydrides to install acyl groups. You could use an acid chloride, though. So I'll get you guys started there. You can kind of try to piece it together backwards, but adding on that acyl group will be your last step. And if you go through your reaction or your lecture notes, you should be able to come up with a decent solution for it. All right, I think what we're going to do is just cut out a little bit early today. I know, it's shocking. Make sure that you do get started on the sapling homework, because we will continue on later this week on to chapter 22.